And if you didn't read that, that was true. All right, so look at this. You should know improper fractions look like this, where the numerator is either bigger or the same as the denominator. Proper fractions have a smaller numerator, right? The same applies pretty much with rational functions, and which is the next unit, but it's related to what we're doing now. Look, proper rational function has a lower degree in the top. The denominator here is degree 2. What's the degree of the numerator? And so that's proper to have a lower degree in the top. This is a degree 1 denominator. This is a degree 0 numerator. So it's also proper. Whereas this one is degree 1 over degree 1. That's improper because it's supposed to be smaller than the top. And that's bigger than the top, so it's also improper. Okay? So look at this. If you do have an improper rational function, you can always do division to rewrite it as a polynomial plus a proper rational function. Look at this. With numbers, this isn't much of a division problem, but if you divide 7 by 2, 2 goes in 3 times, which gives you 6, remainder 1. And you're used to saying, oh, well, that's 3.5, but before that, you learn to get a remainder. And then you put the remainder over the divisor to get the 1/2, yes? But look at this. The point is, if you have an improper fraction, you can write it as a whole number plus a proper fraction. And so that's the idea here. I want you to equate polynomials with whole numbers. All right? And so once again, you can always do this. If you had a larger polynomial divided by a smaller, you can do the division and get it in this form, which is what we're going to want to do in the next unit. So look at this. We're about to do long division. If you do long division with numbers, it looks like this. Polynomials, it'll be a similar process. One thing to note is, like here, to start this, you say, okay, 5 goes into 9 once. 1 times 5 is 5. Subtract, right? And then you get to 4, bring down to 6. And then you keep going. 5 goes into 46 9 times. 9 times 5 is 45. And you subtract, and you keep going. So here, we're going to do that with this. So set up your long division. The 2x minus 5 is your divisor. So put it out here. On your notes, write this down. And then put the 6x cubed plus 17x squared minus 4x plus 16 inside. That's how you set up long division. Now listen, this is not terrible. It's kind of long, but it's not terribly hard. You just have to focus on the right part of it. What you focused on is just the first term of both these. Okay? You just say, okay, what do you multiply 2x by to get 6x cubed? Well, the answer is 3x squared, yes? So that's what you put up here, 3x squared. And then you multiply that 3x squared times that whole thing. Okay? So 3x squared times 2x is 6x cubed, like it should be. You're trying to max that. And then 3x squared times negative 5 is negative 15x squared. Okay? And then you subtract. Listen to me. I like to show my subtraction by just putting parentheses around it and putting a subtraction sign on front. Other teachers would have you change all the signs and add. I don't care which way you show the work. I like doing this way because then you don't mess up your work. If you change the signs and add, then you can't tell if what the original signs were. But the bad thing about this is people sometimes mess up and they'll put like a 2x squared when they're supposed to really remember that's plus 15, right? So there's drawbacks to both approaches. I'm serious though, listen, subtracting sign numbers is the arithmetic people have no trouble with, which is why I'm dwelling on it. That is become plus 15, so that's 32x squared right there, yes? Bring on the next term. All you really need here is as many terms as you're dividing by. Our divisor is a binomial, so you need a binomial, right? All right, so now you repeat the process. 2x times what would give you 32x squared? 16x, yes? And then what do you do to 16x? Multiply by the whole binomial. So 16x times 2x is indeed 32x squared, like we wanted it to be. And then 16x times negative 5 is negative 80x. And you subtract. And that works out to negative 24, actually. 24x. Bring down the 60. And what's the next number in our quotient? And then negative 12 times 2x, negative 24x. Negative 12 times negative 5 is positive 60, which means when you subtract, you get a remainder of 0, which will not always happen, okay? It doesn't always divide evenly. Now, the directions here, though, said factor it completely, which means that better have worked out to remainder 0. Listen, just one little thing. When I divided 7 by 2, I got 3 remainder 1, which told us 3 is not a factor, right? 3 times 2 is not 7. And so I'm saying it has to work out to remainder 0, otherwise it's not a factor. This one, anyway, it is. Now we need to take this and factor it more. It's just a quadratic, so we're just going to factor it using your Algebra 2 skills. I'm giving 3 options. I can show the factoring just by guessing and checking, or by splitting the middle term, or by the box method. Which way do you want to see? Split the middle term sounds good to me. So you start out the same way as the box method, actually. You multiply a times c, which is the 3 times negative 12, and you get negative 36. Okay? And then you put the middle term here, 16. And so you're looking for numbers that multiply to be negative 36, but add to be 16. Which one's going to exactly how you start the box method? What are our numbers? Can't hear you. No. It means multiply to be 36. You can do it. Now 12 and 3. And look, they have to be opposite sign to get a negative, which means they need to subtract to be 16. Yes? 18 and 2. There we go. Now, one of them has to be 1 to make it add up correctly. All right, we have it. What those numbers represent is how you split the middle term. So you come down here, the 3x squared stays there, the 16x splits into negative 2x and a positive 18x. Okay? And then you factor by grouping. And so by that I mean you look at this as 2 separate binomials. The first one has a common factor of x, which you factor out. Yes? The second binomial has a common factor of what? 6. Positive 6 because the leading coefficient is positive, so put a plus 6 there. And you take 6 out of these two terms, you get 3x minus 2. And then you take 3x minus 2 out of both of those, and here you're left with the x, and here you're left with the 6, and you have factored it. And that one I think was a good candidate for doing something other than guessing checking, because 12 has a lot of factors, and if you're guessing and checking, there'd be a lot of different possibilities. It'll work, but I would have done something other than like this. All right, let's write the answer. And by the way, in all this, we're going to call the polynomial our dividend f of x, and the divisor we'll call g of x. Okay. And so now the goal here was just to factor f of x. Yes. So. Okay. Great. I just lost my cursor. So write this out, what I'm saying. I'll write it as soon as I can. F of x equals x plus 6. Wait, I got it. So our answer is that f of x equals x plus 6 times 3x minus 2 times what other factor? 2x minus 5. And by the way, our polynomial was a degree 3 polynomial, wasn't it? So you should expect 3 linear factors. Now, it doesn't always work out that you can factor it completely into 3 linear factors. In other words, let's say this thing right here was not factorable. Well, then it would be one of your factors. You just leave it as one of your factors. If you had like x squared plus 5, you can't factor that. So you could have what's called an irreducible quadratic factor. So this time, everything is factorable. We got 3 separate linear factors. When I say linear factors, they're just degree 1. All right, we good? Yes? Up here. that was given it, it told us that was a factor. And so as we did long division, and once again, if it tells you it's a factor, the remainder better work out to 0. So either the problem's flawed and they're wrong, or you messed up the work. Okay? Div, question? Look at this step right here. You have really two terms. This whole thing plus this whole thing. What do they have in common? The 3x minus 2. So you're already factoring 3x minus 2 out of both these. And we take it out of here, you're left with x. And so, in fact, let me go backwards. If you distributed this times the first term, you'd get this. And 3x minus 2 times the second term, you'd get this. So it's kind of weird because you're factoring out a binomial, but that's the basic idea. All right, let's do it again. And you can follow me. I'm not gonna explain anything. I'm just gonna do the work. You try to do it on your own. Let's see if you get the same answer. And I get a remainder of 10. All right. What everyone's done. I'm going to label the parts of this. The thing we divided by is called the divisor. Our answer here is called the quotient. And the 10 is called the remainder. And for this, I want you to explain it this way. We just divided this big polynomial by x minus 1. That's what this represents. And the answer is 4 because it didn't work out evenly. In other words, if you did 3x squared minus x plus 4 times 2x minus 1, it would not equal this. Because there's a remainder. It equals that plus the remainder over the divisor. So put plus 10 over 2x minus 1. I want you to label your answer either like this, that this answer represents that quotient, or just label them f of x and g and just label it with f of x over g of x. By the way, the fact that the remainder is 10 means, listen, if you did do 2x minus 1 times the quotient, it wouldn't equal this, but if you added the 10 back in, it would. And it's like this, watch. We said if I do this division, I get 3, remainder 1, yes? But if you do 3 times 2, you don't get the 7 back. You have to add a new 1, add in the remainder. the divisor times the quotient plus the remainder is what's going to get you back to your original problem. Okay? And so that's always true here as well. This times this plus the remainder would equal the original. But here, we took an improper rational function and wrote it as a polynomial plus the remainder of the divisor, which is a proper rational function. Okay, listen, one challenge here is that the directions are going to change a lot. Here it said factor the thing completely, and it was factorable. We got a remainder 0 here, and then we factored more, so you could just factor it. Here you couldn't. It just wasn't possible. This was not at least not with this. This is not a factor. So just be careful that you follow the directions. All right. Listen, we're doing long division so far, and I think you probably would agree long division is a pain. It's onerous. It's tedious. We don't want to do it if we can avoid it. And so we won't be doing long division again, ever again, if we can avoid it. Except you can't avoid it with this one. We'll do it one more time, because we're going to do synthetic division after this, but you can't do synthetic division on things like this with a quadratic. Okay? So this one's actually better, believe it or not. We'll do this real quick. So we're dividing by the x squared minus 5x plus 6. I'm saying the other process I'm going to show you is synthetic division, and you can use synthetic division when you're dividing by a linear term, like 2x minus 1 or 2x minus 5. You can use synthetic division. You just can't use it to divide by quadratic. And so, which we won't do very often, but sometimes we will. So you'll have to do long division occasionally. All right, what do I start with? X. Yeah. And then you multiply this again. Multiply x times that, you get x cubed. X times that is negative 5x squared. And then plus 6x. And then you subtract. And that becomes plus 5x squared, so it's 4x squared. Minus 20x. Bring down the 4. And listen, like I said before, you divide by trinomial, so you always want to have 4 terms in here. Okay? We need a 4 here now, yes? And multiply through, you get 4x squared minus 20x plus 24. So the remainder is negative 20. One thing I hadn't talked about yet is how to know when you're done with the long division. Okay? And basically, you're done when the divisor is lower degree. I'm sorry, the remainder is lower degree than your divisor. So on these, we're dividing by 2x minus 1. It's degree 1, right? So here, this is, you can still do the division because this is higher degree. If we got here, you can divide 2x into 8x because it's the same degree. When you get down to degree 0, you're done. This one, it's actually abnormal for it to be constant. If you're dividing by a quadratic like this, normally it's like this. Watch. Let's say this worked out to a negative 28x instead. Then my remainder would be 8x minus 20, wouldn't it? But you would know you're done because your remainder is degree 1 and this is degree 2, and you just, x squared doesn't go into just plain x term. So like I said, typically, if you divide by quadratic, you'll get a linear remainder, a binomial from a remainder. It just didn't work out that way with this example. All right, division problem, so we need to write the answer like we did before. In other words, if you divide f of x divided by g of x, the answer is the quotient, the polynomial we got as a quotient, plus the remainder over the divisor. And so instead of putting plus negative 20 over, I'll just put minus 20 over. Over what? There you go. So that is our answer. Labeled like I did. Effectively. Okay. All right. Now, once again, we just did long division for the last time today. From now on, we're going to do synthetic division. And I'll explain the process in a second. First, look at this. If I did this long division, the numbers here, the coefficients, are 1 x cubed, 3, 2, negative 1. You see, that's how you set up the long division. The 1, 3, 2, negative 1 are the coefficients from the polynomial. Right here, If it's x plus 2 you're dividing by, you actually put the opposite here. Okay? And then look at the quotient. It was 1x squared plus 1x. And you get just numbers here that represent 1x squared plus 1x. And I'll explain it. We'll do an example, obviously. I'll walk you through it. And then this last number here is the remainder from long division. So, much less work here. Yes? Here, let's, and this is in your notes, but I'm going to explain it here. So here, let's just set this up. First of all, I want you to call this x minus c that we're dividing by. And when we set it up, we use c, actually. So I put a 1 here. Yes. And it's really kind of the same idea as what we were talking about before. In other words, if I told you x minus 1 is a factor, then the number 1 is your 0, right? So the 1 is the related number that's related to that binomial. All right, so now you just put the coefficients for the polynomial across here. So 6, negative 2. Now listen, you need to have no gaps here. By that I mean this is a degree 4 polynomial. You should have 5 terms if you have a complete polynomial. You'd have a degree 4, 3, 2, 1, 0, which we have that. So there will be times when you need to put a 0 as a placeholder. Well, we don't need it here because, like I said, our problem already has a degree 4, 3, 2, 1, and 0 term. All right, so leave room for another row of numbers under that. You start the process by just bringing down the first number. Everybody okay on the setup? Listen, it's a really easy process. You start by multiplying whatever number is here on the bottom times c. That gives you 6. And then you add. And you repeat. Multiply this number on the bottom times c. And you add. So multiply the 12 times c. And you add. And then multiply that times c, and you add. And now we always box that last number. That last number is going to be a remainder. And then this over here represents your quotient. I mean, that's this whole thing. Look, we just did another division problem, so I want the answer expressed the same way. In other words, we divided this by x minus 1, and the quotient was 6x cubed plus 4x squared plus 12x plus 3. I'll explain how I know that's what it is, but these numbers here represent your quotient. And the remainder is 0, so that's just it. Listen, there's two ways to figure out the fact that this is x cubed right here. One way is the simple fact that, look, let me go back. If you look at this division problem, if you divide a degree 3 by a linear, you get a degree 2 answer. If you go back, when we divide a degree 3 by degree 2, we got a degree 1 answer. Usually, we're dividing by linear, so like here, when you divide, your answer is 1 less degree, right? And so with synthetic division, that's always going to be the case. If you divide, if this original was degree 4, then the answer is going to be degree 3. Just every time. Or, realize this, look at this. Right here's the remainder, so right before it is a constant, before that's the linear term, then the squared term, then the cubed term. And just work your way back up. So that must be the 3, the constant, then that's the x term, the x squared, and you just work your way up. Okay? All right. Let's do it again. Now, this one's a little bit tricky. Write this down. I want you to realize those two binomials have the same x-intercept, don't they? If you plug negative 1/4 into both of them, they have the same x-intercept. They're not the same line, but they have the same x-intercept. So we'll use negative 1/4. And then, do we need any zeros when we set this up? No, it's degree 4. It has 5 terms. There's no terms missing, so just put your 5 numbers. And just go through the process. Bring down the first number. Then once again, multiply and then fourth of 8 is 2, so that's negative 2, and add, you get 36, then multiply, you get negative 9, and add, multiply, you get 1, and add, and multiply, you get negative 1, and add, and the remainder turns out to be 2. And once again, we're just doing division, so I want you to write the answer the way we did with the other division problems as the quotient, which is 8x to the power of what, Chris? Yeah, because the original was degree 4, so this is 1 degree less. And then plus 36x to the power of 2 minus 4x plus 4 plus the remainder over the divisor. What was the divisor? There you go. And that is our answer. Yeah. Yeah, I showed that just to show kind of where the 1/4 came from, but really you just set this equal to 0 and solve to get the negative 1/4. All right. This one, it's a slightly different directions. It's the same process though, so real quick, you do this as quickly as you can. Try not to look. Just check your work if you need, but this should take very, very little time. So you got a remainder 5. Listen to me. If you did everything I did and left it just like that, I can't give you credit. Because I know I said to box a remainder, but you could very easily just be boxing that number because I told you to not remember what it means. So I'm saying, it says find the remainder. Either call that the remainder, then I know that you know that it's remainder, or off to the side, write your answer and box it separately. But somehow indicate to me you know not just how to show the work, but what the work means. Okay? If it asked for the quotient would be x squared plus 4x plus 6, right? But I didn't ask for that. So like this, not hard, just make sure you understand the directions and answer the question, because they'll vary the question. All right, now look at this. This is the problem we just did, and I just want you to see it again. If we'd done long division, then, like I said, the 146 would represent a quotient of x squared plus 4x plus 6. And if you did all the long division, your remainder would have been 5, just like you said. All right? It's just less work here. In the next unit, I think Thursday we'll hit the next thing. Each problem, you have to do division 3, 4, 5 times. So I'll leave it to you whether you do long division or consecutive division 3, 4, or 5 times for the problem over and over again. But, you know what I'm going to choose. All right, so look at this. The remainder theorem, I think it's very remarkable. It says that, when you do this division we're describing, then the remainder you get actually represents the value of the function at c. So let me go back to the problem we just did. Look at this. The remainder was 5. According to the remainder theorem, this 5 represents f of what? But what is c? 1. Right? This is x minus c. This is c. And it turns out this equals f of c. Well, let's check it. How do you normally find the value of a function? You substitute. So here, watch. You do 1 cubed plus 3 times 1 squared, right? You just substitute and evaluate. That's 1 plus 3 plus 2 minus 1 is 5 indeed, yes? Which means with polynomials, you never have to actually substitute again if you don't want to. you can do this process. This process, I've called it synthetic division. It's also called synthetic substitution, because that final number is the remainder from the division, and this is the quotient still, but it also represents the value of the function at C. That's what I'm saying. And, here it was really easy because it's just 1, so this was easy. But what if it was, 20, 23? Who wants to do 23 cubed, right? You don't need to. You can just do this. And with 23, it'd be harder, but it's much easier to do this with the 23 than it is to do this with the 23. So here, by the way, I have the directions on there for synthetic substitution. This exact same steps, the same exact process. You just interpret it different. Here, let's do this one. And first, I want to find f of negative 2 by hand. So we do normal substitution one more time, and then after that, we'll always do this synthetically. Negative 2 cubed is negative 8. What does this work out to? 8, right? You get 4 times 2 is 8. And then minus 7. So the answer is negative 7. Okay? So f of negative 2 turns out to be negative 7. Fine. Now let's go up and do synthetic division, because it says up here, the directions say find the remainder using this division problem. So use negative 2 because it's divided by x plus 2. 1, 2. I need a 0, don't I? There's no x term, so you put a 0x in the minus 7. You should catch that. If it's degree 3, you should have 4 numbers there. If you don't, you'll get the wrong answer. All right, bring down the 1, div. What goes here? Tell me what goes here. In here. And then multiply 0 times that, you get 0, and add, you get 0. 0 times that is 0 again, and you get negative 7, which is your remainder from the division, but it is the value of the function at negative 2. So I'm saying to answer part B down here, you could have done it normally, like I said, or done it synthetically. And so that's what the remainder theorem says. The remainder from the synthetic division is the value of the function at that number at C. Okay? Now, another theorem, the factor theorem. It's not much of a theorem. All we're saying, look, when I say the word factor, that means you divide them evenly, right? The remainder is 0. But that means when you do long division, or any kind of division, the remainder should be 0. It also means that C is a root, right? So here, look at this. This next one says determine if these are factors, and then write in factor form. They're factors, so the remainder is 0. Just do your division again. We're going to do synthetic division. So like I said, same process, same skill, slightly different phrasing of the question. All right, bring number 4. Jacob, walk us through it. What goes here? Okay. And then? And then multiply, you get 34. Add, you get 15. Multiply, you get negative 30. Add, you get 0. Which tells us that x plus 2 is a factor, right? Listen, what we have as a quotient is quadratic. I want to show you a couple different options as to how to finish this problem. One thing is go with the idea that, maybe x minus 3 is a factor. Maybe not. We didn't say it is, but watch. If you're trying to factor this, and you know one factor, that makes it much easier, doesn't it? So if this is a factor, then you're going to have a 4x here, because 4x times x is 4x squared. And if it's minus 3, it has to be minus 5 to work out to the plus 15, yes? So it's either this or nothing. I say it that way because this still has to work out to the middle term. Does it? That's negative 12x. That's negative 5x. It does add up to negative 17x, so it does actually work out. which means we're done. The goal is to write the original polynomial in factored form. Well, it turns out the factors are x minus 3, 4x minus 5, and what, Jeremy? Anybody? No. Okay. But we started by checking to see if x plus 2 is a factor, and the remainder being 0 told us it was, right? And if it, frankly, if it hadn't been, then we would have tried the x minus 3 next on the original. By the way, let me show you another way we could have finished this. Once we got to the quadratic, here, watch, I'll set it up over here. Let me use, set up the quadratic here. And then I could have divided by the x minus 3, put a 3 here, and here. Bring down the 4, multiply, you get 12, you get negative 5, multiply, you get negative 15. The remainder works out to 0. And sure enough, that would have given you the 4x minus 5, wouldn't it? And so, of course, it could have been the case that x minus 3 was not a factor, in which case we simply would have had a factor of the same. It was, so it was easier. Okay? All right. This one is actually easier, I think. Just slightly different directions now. Here, do the division. No. But you do the division and use the factor theorem to interpret it. Listen, you're always going to be doing this in vector division, unless you're divided by quadratic, okay? Which means, showing the correct work is only half the battle. Giving the answer expressed correctly can be a challenge. Linda, can you tell me what I'm supposed to write in this question? F of x equals what? I mean, it was a factor because the remainder is 0. So I'm supposed to express it like this. What's my divisor? Times and there you go. Now, it was a conditional statement in here. It said if x plus 1 is a factor. If it wasn't, you would just stop and say, well, it wasn't a factor. Listen, it could have said factor completely, right? And we had problems with that was the directions. And if it did, then you'd be factoring this thing. But this one, it just said do the division and express it this way. Tell me this. Look at this next part. If c is negative 1, that means we're trying to figure out what is f of negative 1. Well, what is f of negative 1? Arsham? Look at our work up here and tell me what is f of negative 1. You're making it much harder. 0. The remainder theorem says that the remainder you get by dividing by x plus 1 equals the value of the function at c, at negative 1. So if you divide by x minus 1, x minus c, you're really also doing f of negative 1, f of c. So the answer is yes. Negative 1 is a 0 of the function because x plus 1 was a factor of the function, right? But I'll put it this way. Yes, negative 1 is 0 of the function because f of negative 1 worked out to 0. If you wanted to, once again, you could plug negative 1 in and do all the math, and you'd get 0. But you don't have to. Here, we'll do this one. It's not going to work out. We'll be quick, okay? Bring that down, you get negative 2, add you get 3, multiply, you get negative 3, add you get 1, multiply, you get 1, add you get 4. Hope I didn't make a mistake. So, it's not a factor. And therefore 1 is not a 0. Because f of 1 equals what? 4, which is not 0. So x minus 1 is not a factor because the remainder is 4, which is not 0. And 1 is not a 0 because f of 1 is 4, which is not 0. All right, one last little thing. I can go back to it if you didn't finish copying. I've been saying this, but it bears repeating. Whatever your degree is, that's how many solutions you can have. It's also how many factors you can have. And your factors could look like that. They could. What are the roots of this polynomial? Square root of 2, 7, negative square root of 3, and positive 2y. Now, if you multiply those out, you're going to get an ugly polynomial. What would the degree of our polynomial be? 4, right? It's a degree 4 polynomial, so it has 4 roots. Of those 4 roots, how many are real roots? Jacob? Which of those is not real? Jacob? I can't hear you. Yeah. And so, like I said, we've been saying, if it's degree 4, have at most 4 real roots, because some of them can be imaginary. All right. That is it.